Hello, ladies and gentlemen. What we will be discussing in today's lesson will be how you graph exponential functions. Now, exponential functions have a whole widespread array of applications that they can be used for, from predicting population growth to radioactive decay to all kinds of applications with money, finances. But what we are going to be focusing on today primarily is how you graph an exponential function. Now, what we're seeing here is as kind of like a parent function is f of x is equal to a to the x power. Now, I want to be clear, this isn't really a true parent function. If you looked up what the parent function of an exponential equation is, it's probably going to say 2 to the x power. And the number that we substitute in for a, we call that a base. The reason why we use 2 as the primary kind of number in a parent function for an exponent is the fact that we can't actually use 1. Since x is in the exponent position, if I say 1 to the 3rd power, 1 to the 8th power, 1 to the 5 millionth power, it's still just 1 because 1 times itself is always 1. And if I just say y is equal to 1 all the time, that's just going to give me a straight line where y is equal to 1. So that's why we don't use 1 as the base of an exponential equation or as an exponential function. Now, the next thing that you're seeing here on the screen is that the domain of an exponential function is going to be all real numbers. But the range, however, is not. The range of a basic exponential function cannot include the number 0 or anything below 0. And let me give you a brief explanation as to why. So if I say, let's say 2 to the 4th power, or 2 to the 6th power, or whatever the case is, those are going to give me some positive number. So what if the exponent number was a negative number? Okay, well, let's try a negative number. If I say 2 to the negative 2 power. Well, 2 to the negative 2 power, if I use my rules of exponents, we can't have negative exponents. So that is equivalent of saying 1 over 2 squared, which is 1/4. Positive number. If I say 2 to the negative 3rd power, that would be equivalent of saying 1 over 2 cubed, which would be 1/8. Again, a positive number, something bigger than 0. If I say 2 to the negative 4th, keep making the numbers negative, we're going to get 2 or 1 over 2 to the 4th, which is the same thing as 1 over 16. Now, these numbers are all positive, but they are approaching the number 0. 0. And that's what's going to happen. It doesn't matter what negative exponent that I put into it. It's going to what happens using the rules of exponents is that we kind of rewrite it as a fraction, as 1 over that number with a positive exponent, which will always produce a positive number, something bigger than 0. Now, the bigger the negative exponent gets, the closer it approaches to 0, but it never actually gets to become 0. That's why the range is going to be something greater than 0 all the way up to infinity. And as a result, we wind up with a horizontal asymptote where y is equal to 0. So those are some kind of introductory ideas of what a exponential function does. Now, what we will be seeing here, one of the primary skills that we're going to be practicing first is going to be, can you graph an exponential function? Now, just like every other function that we've seen, the same basic transformations will apply to these as well as any other function that we see. So what we have here, in order to graph an exponential function, up here at the top, we have 3 basic points. We would refer to these as key points for every exponential function. If you can find those 3 points, then you will be able to graph any exponential function. Okay, and I have 2 here as an example that we're going to try it on. Now, right underneath there it says if the base is larger than 1, then we would refer to that as an increasing function. That would be something that would represent like a population that is growing. If I say the base is smaller than 1, meaning it's a fraction of some kind, that would give us a something that was going to be decreasing or going down. That would be something that would work great if we were talking about radioactive decay. That would represent where something is decreasing over time. Okay, but that's not, we're not trying to talk about applications right now. I'm just saying that's what they would probably be used for. Right now we want to try and graph these suckers. So here, the base of this function h of x is 4. So what I'm going to use is I'm going to use those 3 key points in order to be able to graph what this basic function looks like. So if I say 0, 1, that is kind of a non-negotiable one. That's going to be used for every basic function that we have. Pardon me. The next key point is going to be the number 1 and whatever the base is. In this case, the base is 4. And the third key point is going to be the number -1 on the x-axis and whatever the reciprocal of the base is, which in this case would be 1 over 4. So those 3 numbers, if I just plot those 3 points, then I should have enough to give me a good sketch of what the function should look like. Now again, because this is a basic function, we will have a horizontal asymptote at y is equal to 0, which is essentially the x-axis. And let's go ahead and plot our points. We have 0, 1, we have 1 and 4, and -1 and 1/4. Now I'm going to just kind of approximate where that one is. And because a, the base, is greater than 1, it will be increasing, and there is the sketch of what the exponential function would look like. No big deal. Here we have function p on the right that says p of x is equal to 1/3 to the x power. Now here the base is a number that is less than 1. So here we're going to see something that's decreasing. So it should go down from left to right. And again, we want to identify what are the 3 basic points. So 0, 1 is always going to be used for an exponential function, or at least a basic one. And 1 and whatever the base is, so I'll say 1 and 1/3. And then -1 and the reciprocal of the base, which the reciprocal of 1/3 is just 3. So those are the 3 key points that I would use to graph this particular function. And again, because it's a basic function, there's no transformations being applied. It will have a horizontal asymptote at y is equal to 0. So let's go ahead and plot these points. 0, 1 again, 1 and a positive 1/3. So I'll just estimate about there. And -1 and a positive 3. So again, if we were to connect the dots, it will kind of come down through the 3 points and level off at the horizontal asymptote. And there we go. There's the sketch. Now, what we will be doing is we want to know what are the basic functions of the exponents that we're trying to graph. Because if I can get these 3 key points, then I can do any transformations that I need to in order to graph a transformed exponential function. So that's why we need to know how do we identify those 3 points of any function, of any basic functions. That way we can therefore transform them. And that's exactly what we see here. We have a function that says y is equal to 3 to the x minus 2 power minus 3. Now, what I see here, in other functions, we would generally see that in parentheses. That is telling us that we have a horizontal translation, meaning it will slide side to side. The minus 3 here is what we would, in every other function, that would be our vertical translation. Meaning that tells us that we move up and down. So the x minus 2, the horizontal translation, that's basically going to tell you we're going to take whatever the basic function is and shift it 2 spaces to the right. Then the minus 3 at the end says we're going to take whatever that is and move it down 3 spaces. So I want to start. I want to know what is my base function? Well, my base function is just y is equal to 3 to the x power with no transformations. So using the three key points, 0, 1, the number 1 and the base, which is 3, the number -1 and the reciprocal of the base, which would be 1/3. I'm going to go ahead and plot these points on the graph. So 0, 1 right here, 1 and a positive 3 right here, and -1 and a positive 1/3 is approximately right here. And of course, that would have a horizontal asymptote of y is equal to 1. So we could kind of draw our curve going through those 3 points. Now, I don't want to draw the curve on here just yet because I want to see how are we going to transform them. Now, the transformations we can actually do 2 different ways. Let me pick a color that'll show up good here. Mathematically speaking, I can take the 3 basic coordinates that we have and apply the transformations to those. And I'm going to go ahead and do that first, just so we can see what the coordinates would be. Then I will apply the same transformations to the graph that we have at the right and see, do the coordinates that we got through mathematic transformations match the graphic transformations? And ideally, they will. So the horizontal translation, this right here, the -2, because it says -2, that's the horizontal shift. That's really going to take the function and move it 2 spaces to the right. So because it's saying move 2 spaces to the right, what we're going to do is we're going to say add 2 plus 2 to all x numbers. I'm going to add 2 to all of the x coordinates of my basic function. And I hope the green, I don't think I like the green. Let me pick something that will hopefully show up a little bit better. So we're going to take all of the x coordinates and add 2 to them. So 0 plus 2 will give me an x coordinate of 2 here. 1 plus 2 will give me an x coordinate of 3 here. And -1 plus 2 will give me an x coordinate of 1 here. Okay, so now let's see what the y coordinates would be. Well, the -3, that transformation says to subtract 3 from all of my y numbers. Whatever the y coordinates are, we're going to subtract 3 from them. So if I say 1, going back to the basic functions, the first one, 0, 1, if I subtract 2 from that y coordinate, 3 from that y coordinate, I'm going to say 1 minus 3, which will give me a -2 for that y coordinate. 3 minus 3 will give me a 0 here, and 1/3 minus 3 will give me -2 and 2/3 for that y coordinate. Now I'm going to go ahead and plot those points. So 2, -2 will give me a point right here. 3, 0 will give me a point right here. And 1 and -2/3 will give me a point about right here. And the -3 of the function says that I should have a horizontal asymptote where y is equal to a -3. So now let's do the vertical. Now let's check the transformations on the graph itself. Okay, so the transformations say 2 to the right and 3 down. So from this point right here at 0, 1, if I go 2 to the right and 3 down, we wind up at the same coordinate that we calculated before. And we kind of see, if you say 1, 2 here, down 1, 2, 3, we wind up at the coordinate 3, 0. And we would do the same thing with the last one on the left. If I say 2 to the right and 3 down, we will see we'll wind up at the same coordinate that we calculated just through a little basic addition. So let me go ahead and clean this up just a tad. So the stuff in red, that would be the coordinates of the basic function. And the ones that are in a kind of like a darker red, kind of like a magenta, I guess, rusty red, I don't know, that is the transformed function that we will see here. And I don't really care what the other points are. I just want to see those 3 points. because with those 3 points, we can get a good sketch of what the graph should look like. And there we are, we're done. So every function that we've ever seen follows the same transformations, and this one is no different. Okay, exponents are no different. So here what we have, this is going to be the last example that we look at. Here we have a basic function, or I'm sorry, not a basic function, but we have y is equal to 1/2 raised to the negative x power, and then we're saying plus 4. So here we also see 2 transformations. This negative sign says that is reflected. Now in this case, this is not going to be reflected across the x-axis because of where the negative sign is. That's actually going to reflect it across the y-axis. That will be a side-to-side reflection. Reflected across the y-axis. And this plus 4 says we'll move up 4 spaces. Now again, what I want to do for all of these functions, at least until I have done enough to have a good idea of them in my head, we want to follow this same process. I want to know what was my basic function without any transformations. What would it be? And in this case, with no transformations, it would be 1/2 to the x power. Now the base in this case is a number that's smaller than 1. So that would give us a function that should decrease as we move from left to right. Pardon me, I'm sorry. So our basic points are going to be 0, 1, 1, and whatever the base is, in this case 1/2, and the number -1, and the reciprocal of the base, and the reciprocal of 1/2 is 2. So those are the 3 points that we would have for our basic function. So let's go ahead and plot those on the board. So 0, 1 is right here. 1 and 1/2 is about right here. And -1 and 2 will put me right here. So you can see, yes, that is going to go down as we go from left to right. So now, let's see what we're going to do. Here, what we're going to say is, if I'm reflecting across the y-axis, remember, if I reflect across the y-axis, I'm moving side to side. So side-to-side movement is really going to do something to my x numbers. So what this transformation is telling me to do, it says multiply my x numbers by -1 to show that they're going to be reflected across the x-axis. So 0 times -1 is just 0. 1 times -1 will be -1, and -1 times -1 will be a +1. So there are the x coordinates of my transformed function. And this one, of course, says to add 4 to all of the y numbers of my basic points. So 1 plus 4 will give me a 5 here for the y coordinate. 1/2 plus 4 will give me 4.5 for the y coordinate here. And 2 plus 4 will give me a y coordinate of 6. So now let's plot those points, and then we can compare, does the ones that we calculated with the transformations match the actual movement of the function from the basic function to the transformed function. So 0, 5 will put me 1 point here. -1 and 4.5 will put me about right there. And +1 and 6, +1 and, we're almost out of room here. 5, here's about 6 right there. Okay, and this +4 says we are going to have my horizontal asymptote at y is equal to +4. So what we'll do is we'll follow the horizontal asymptote through those points, and there is the transformed function graphed. So what we'll see, let's check. So I'm going to start with 0, 1. What we're saying is reflected across the x-axis. Well, we don't reflect if we're on the line of reflection. So that just says move up 4 spaces. So from here, 1, 2, 3, 4, that works. So what I'll do here, let's look at this one, the one at +1 and 1/2. If I reflect that across the y-axis, I'll put here, and then if I go up 4 spaces, 1, 2, 3, 4, yeah, we wind up right where we calculated it to be. And let's check the last one at -1 and +2. If I reflect across the y-axis, I'll wind up here, and then I'll move up 4 spaces, 1, 2, 3, 4, and yep, that worked out pretty well. So we have our final transform function, and all is good in the realm of graphing exponential equations. That's going to be the last example that we're going to practice right now. If you have any questions, again, just as always, make sure you write them down in your notes as you're following along. If you have questions, make sure you bring them to me in class. Don't be afraid to come to tutoring. See me before class or after class. I'll be happy to help you answer any questions that you might have. And until then, hope everybody's doing well and see you in class soon.